So in this example, we have a balloon that is expanding. You can see the balloon over here. There are two different cases. One is a balloon that's just in this infinite surroundings, and then another case where the balloon's inside a box. And we're asked for part A is what's the minimum amount of work that must be done by the air in a balloon when it's inflated from one volume to another volume against a constant external pressure of 1 atmosphere, absolute. So it's like a balloon just out in the atmosphere. And then for part B, again, the balloon is in a box, and the box volume is given here. And we're asked to find how much work would be required to inflate the balloon between the same two volumes, so the same volumes up here, if the external absolute pressure, so this is the pressure in the box, is given by this expression. So as the balloon volume increases, this gets smaller and smaller, so the external pressure gets bigger. That sort of makes sense. As the balloon here gets bigger, then the volume of the surrounding air gets smaller, and you would expect that the pressure would increase. All right, so let's start with part A. What's the minimum amount of work that must be done by the air in a balloon when it's expanding? This is PDV type of work, right? So we're changing the volume against a constant external pressure. So the work done by our system, and our system here is the balloon, or is the air in the balloon. Okay, so that's our system is the air inside the balloon here. That PDV work will be equal to the integral of the pressure inside the balloon times the change in volume as we go from some initial volume, call it V1, to some final volume, V2. So that's the work being done by the air inside the balloon. So in this case, the external pressure is just 1 atmosphere, so we can pull that pressure outside the integral because it's a constant. You can only do that if the pressure is a constant. And then, of course, this just becomes P times V2 minus V1 when you work out that integral. So we can plug in the numbers for this. We're told that the pressure is 1 atmosphere, absolute. And the and by the way, this should be we just use that pressure. We should convert that over to pascals. So that will end up being 101 kilopascals absolute. V1 is 0.100 liters. The conversion, let me just show the conversion here. The conversion between liters and cubic meters, this is an easy one to figure out, is it's 0.001 cubic meter per liter, or 1,000 liters for 1 cubic meter. Right, so that ends up becoming, what is that, 1 times 10 to the minus 6. No, I'm sorry, I made a mistake there. That should be 1 times 10 to the minus 4 cubic meters. And then V2 is our 1.85 liters. So again, let me just write this one a little differently. 1 cubic meter is 1,000 liters. So that'll be 1.85 times 10 to the minus 3 cubic meters. Right? So then we can go ahead and plug in the numbers, and what you'll get is the work done for this particular case comes out to be 177 joules. So that's the amount of work that the air does on the surroundings as it expands. Now for part B, we now have the balloon in the box, and we still have the same kind of system here. But in this case, the pressure is varying. So to find the pressure work, we still start with the same equation here, but the pressure is now, it varies with the volume. So it's still PDV work, but now I'm going to substitute in for the expression for pressure. Okay, so that's what our expression looks like. Now the numerator, these are all constants up here. P naught's a constant. We're told what that is. V naught is a constant. That's given right here. And the V box is a constant. That's given right here. And so those can come outside the integral. So let me just write that out. So that'll be P naught times V box minus V naught integral v1 to v2 dv over v box minus v. So you have to solve that integral. Well, that integral is like a natural log, right? It's like a dv over v kind of term. You can solve that through a substitution to make it look like, dx over x, that kind of thing. So you can solve that, and when you do that, that is your calculus. When you do that, you'll get the following expression. It's a natural log v box minus v2 all over v box minus v1. Okay, and then we can go ahead and plug the numbers in. I won't write out all the numbers here, but when you solve it all out, the work done by the system in this case comes out to be 194 joules. So it's a little bit larger than here, right? So when the balloon is inside the box, the work is a little bit larger. And the reason for that is because as the balloon expands, the pressure in the box goes up, right? You can see that here as V, that's the volume of the balloon, as that gets bigger, this denominator gets a little bit smaller, which makes the pressure a little bit larger, right? The volume of the balloon will never be bigger than the volume of the box. So V is always less than V box. But the pressure gets larger, and so there's more work that needs to be done for the balloon to expand a little bit further because the exterior pressure is increasing. And so that's why we have larger work here. So it's a good idea after doing the calculation to make sure it makes sense. Should this be larger than that value? It does make sense that it should, right? We understand physically why that should be the case. The other thing that would be worthwhile is to consider the special case when the box is really large. So let's say V box, instead of being this value, is some really huge value. Okay, so let's say it was infinitely large. Okay, what would happen in that case when V box is really, really big? So you look at the limit when V box is really big, and what that will end up looking like is you'd have to look at this expression, or actually I suppose we could, well, yeah, let's look at it here. When V box is really big, this would be like infinity over infinity, so you have to use L'Hopital's rule to simplify it. And so then that becomes, let's just take a look at that for a moment. That would be P naught all over just 1, right? So in the limit, as V box goes to infinity, that integral, I'm just not going to rewrite it, but it's this integral here, ends up becoming the integral from V1 to V2 of P naught dV all over 1. So it's just P naught times dV, which is exactly the same as what we have up here, where the P was a constant. Right? So then it would just become P naught times V2 minus V1. So this is in the case where the box becomes very, very large, and what ends up happening is this result goes back to being the same as the original calculation, which again makes sense because when the box becomes very, very big, it's like the balloon's in an infinite expanse, right, of atmosphere. So we should end up simplifying down to the original case, which indeed it does. So this is another good thing to do whenever you're given a problem that's, it starts off simple and then it becomes more complex. It's always good to make sure that the more complex problem simplifies back down to something that the more complex case simplifies back to the original case when you make the right assumptions. So that's what we did here, is we just looked at the extreme case when the box was very, very huge. We expect that we should get back the original value, and that's indeed what happens. So two important things I just want to highlight about our problem solving solution here. Number one is just to interpret the result. Why is this one bigger than that? So we did some interpretation of that. And then the second thing was taking our more complex case and looking at a simplified case or an extreme example of that, and then making sure it goes back to the more simple case. All right, we'll end the example there.